Take a look at this problem in section 2.3. This one's trying to expand upon the development of the concept of a limit using an application problem. It says, suppose a spaceship of length L is traveling at high speed v relative to an observer. To the observer, the ship appears to have a smaller length given by the Lorentz contraction formula, where we know, and I'll go ahead and write it down here, L is equal to the original length, L sub 0, on the square root of 1 minus, and v is representing the velocity it's traveling at, so v squared over c squared, where c is the speed of light. Excuse me. Okay, so now part A, it's asking us to observe the length L if the ship is traveling at 50% of the speed of light. So what we're given in part A here is that v is equal to 50%, or I would prefer to say 1/2 the speed of light. Therefore, the length that it would appear would follow the equation L is equal to whatever the original length is on the square root. And inside of this square root, we're going to have 1 minus, and since the velocity is 1/2 c, I'll say, well, I'm going to have 1/2 c quantity squared over c squared. Now, whenever I'm simplifying this out, I can say, well, this is going to give me L sub 0 on the square root. And inside of this, I know that the c squared over c squared would cancel out, but I'll be left with 1 minus 1/2 squared. Well, 1/2 squared is 1/4. So I'll have the square root of 1 minus 1/4. That's going to end up being the square root of 3/4, because it's 4/4 minus 1/4. I would say that this is equal to L sub 0 times the square root of 3/4. And then most people would go ahead and simplify that and say, well, we could call that L sub 0 on the root of 3 divided by the root of 4, which would be divided by 2. You could do that. You could also move the square root of 3 in front of the original length, whatever you would prefer there. Now, I have this problem showing the solutions, and you'll notice they do want the answer I have right here. They left the square root of 3 over 2 out in front, multiplying the L sub 0 like that. Doesn't really matter how you show it. It'll accept any format. Now, part B here is asking us what the observed length of the ship is if it's traveling at 75% of the speed of light. Okay, so I keep going in this pattern. So part B here, I would say that the observed length L is equal to the original length on the square root. And now I'll have, if it's 75%, I'll think of that as 3/4. So 1 minus 3/4 c quantity squared over c squared. Again, the c squareds are just going to cancel out there, and I'll be left with L sub 0 on the square root of 1 minus 3/4 squared. Well, 3/4 squared is 9 over 16. I'm going to have 16 over 16 minus 9 over 16. This is going to be L sub 0 times the square root of 7 over 16. 16 minus 9 is 7. Keep the denominator of 16. I'm sure you could leave that as the square root of 7 over 16 times L sub 0, or you'll see what they've done here is they've simplified that to be a 4 in the denominator with that square root of 16. Now, for the next part here, if I look at C, it says in parts A and B, what happens to L as the speed of the ship increases? Well, you can see that as the speed of the ship increases, that the length is going to decrease. The square root of 7 over 16 is less than the square root of 3 over 2. So the ship is getting smaller as it's approaching the speed of light. We're subtracting more and more from that value of 1 inside of there. Oops. So now I can say, well, all right, for part D here, if I can get this to move down. There we go. So as the speed of the ship increases, the length decreases because we keep on subtracting more and more inside the square root. And then we can say, evaluate the limit, select the correct choice below. If necessary, fill out the answer box to complete your choice. Okay, so whenever we're thinking of that, if I can get this to behave, the limit that they give us is the limit as V approaches C from the left. So for part D here, the limit as velocity approaches the speed of light from the left of this function, L sub 0 on the square root of 1 minus the velocity squared over the speed of light squared. Well, if V is approaching C, then you can go ahead and plug C into it, and we can say, well, this is going to end up being the original length on the square root of 1 minus C squared over C squared. That's just going to be 1 minus 1 in there, and you can say, well, L sub 0 times the square root of 0 in there, and then you'd say, well, all right, that's just going to be the limiting value of 0. So as that's approaching the speed of light, the length of the spaceship is going to approach 0 from the observer, or at least the observer's perspective of the length of the spaceship. Okay, guys, hopefully this makes sense. Let me know if you have any questions.